Hi, my name is Mark Fulling, and today I'm going to attempt to explain how data reaches your phone and how it works when you're traveling over long distances. A couple of months ago, I was traveling down the Pacific Coast Highway between Santa Barbara and Los Angeles when I suddenly realized that the Sun Devils were playing the Bruins. My father-in-law was driving, so being the big fan that I am, I launched the Pac-12 app on my phone and started streaming the game. An hour or so later, I wondered, how has this game managed to stay on and uninterrupted? We've driven a long way. Now, I thought I learned somewhere that cell phones do a thing called a handover, where they switch your call from tower to tower as you go out of the range of one and into the range of another. But I started thinking, that doesn't sound easy even for a phone call. How do they switch this game? It's not like it's on AT&T, it's coming from the internet. I thought this might be a cool topic for this technical presentation. So in order to understand what was happening, we should probably start near the beginning. So let's go back a little further. Not quite that far. This is more like it. Early cell phones. The Motorola flip phone on the left is a first generation. My mom had this model. It would get really hot when you used it and the battery sucked. The Nokia on the right is a second generation phone. I owned one of these sweet Nokias. The biggest difference between the generations is that the first generation were analog phones and the second generation were digital. What do I mean by that? A few weeks ago, Mr. Lundquist talked about analog and digital signals, but as a refresher, and as defined by Newton's Telecom Dictionary, an analog signal is a signal in the form of a continuous wave, varying in step with the actual transmitted information, whereas a digital signal is a discontinuous signal. Now, according to Larry Daniel of Guardian Digital Forensics, the effective range of an average cell phone tower is about 22 miles. Some are much shorter and some are much longer, and that's due to geographical terrain, signal characteristics, and power output. So, in order to cover a large area, like most of the inhabitants of the modern world, towers are placed everywhere. In typical configurations, a tower has 3 120-degree sectors, providing a total of 360 degrees of coverage. To depict what a network looked like over a given area, engineers would use a bunch of hexagons or cells over a map. This is where the term cellular network came from. A hexagon is six-sided, and as I mentioned before, each of these 6 sides would typically be split into 320-degree sectors. So let's say that you were using your phone in the left side of the middle cell and you wanted to drive about 40 miles to the bottom left cell. You will have touched up to 4 different sectors. As I alluded to earlier, and again referencing Newton's Telecom Dictionary, when you go from one cell to the next, it's called a handover. While you're on your call, your phone is communicating with adjacent cells and measuring signal strength. Once a certain threshold is met, i.e., the cell you're heading towards is more attractive than the cell you're leaving, the network will reroute your call from one cell to the next. Early cell phone networks looked a little something like this. Your phone connected to a tower, the tower connected to your carrier's servers. Now, these servers took care of the call routing, the handovers I just talked about, billing, and things of that nature. The server is then connected to the public switching telephone network, which is like a landline in your house. Now you might be looking at this and wondering, where does the internet play into this? Well, with 2G iterations allowed for the option of texting, and that led to very rudimentary data transfers. And then 3G stepped up. I mean, seriously, what good is an iPhone if you don't have data? According to Professor Powell of Mobile Business, 3G networks utilize the same structure of the earlier networks, only from the carrier servers there was a gateway to the internet. Also, 3G were backwards compatible with 2G. 3G was great for a while. Problem was, it couldn't keep up with demand. There were way too many people using way too much data. According to 3GPP, the goals of 4G and long-term evolution, or LTE, were to efficiently use the spectrum available, offer speeds of up to 173 megabits per second, reduce latency as low as 10 milliseconds, create an all IP or packet-based network, and introduce a new interface to implement multiple input, multiple output, or MIMO scheme in order to gain faster downlink speeds. The new MIMO scheme allowed for the use of two multiple access schemes. The downlink, which is from tower to phone, uses orthogonal frequency division multiple access, which optimizes time, frequency, and code division multiplexing. The link from the phone back to the tower, called the uplink, uses a single carrier frequency multiple access, SC-FDMA. MIMO also allows for spatial multiplexing, meaning that 2 or 4 antennas can be used for the up or the downlink. Now, about that handover. According to Qualcomm, the tower that I'm connected to is called the source eNode B. The eNode B decides when to initiate a handover based on signal strength and other parameters like availability. The source eNode B then chooses a target eNode B for the handover. Once the handover is initiated, a handshaking process begins where the source eNode B and the target eNode B transfer security and syncing messages. Then the source eNode B sends my information or end user context along with my buffered data, which in this case is the UCLA ASU Football game, to the target eNode B. Everything is then cleared through the mobility management entity. The S gateway starts sending the football game to the target eNode B. The target eNode B then assumes the role of the source eNode B. And I get to watch ASU beat UCLA. The following slide is a list of the sources I used for this presentation.